Chairman, ladies and gentlemen. I'd also like to extend my thanks to the organisation because this was a very, very kind gesture to invite me to this place. It's been a double-edged sword in that at first I thought, okay, this is probably a bit intimidating. As I sat down, I thought, no, I can really do some amusing stuff here. So it sparked me to dig into the vaults, into a topic which I've been trying to deal with for the past 15 years or so. I've not worked at DAS over 15 years, but fatigue of plastics is something I've been struggling with for a long time. And the title says a critical review of fracture mechanics. I'm afraid you're not going to see that much fracture mechanics. We're going to look at a different parameter, which is the overall killer when it comes to fatigue of plastic, and that's temperature. So, what do I mean by that when I say it's the key element? If we look at this here, this is a very typical example. Glass fiber reinforced nylon 66. Very simplistic. This is a monotonic stress strain curve on the left-hand side of the picture. The blue line represents 23 degrees C, red line 80 degrees C, and the green line 130 degrees C. Easy enough to understand. Yes, you can clearly see the temperature dependency of the material, and this even being a reinforced material. But what's the point? What's interesting? Well, if you draw a parallel to SN, or nominal SN fatigue properties, which is, it's not accepted, but it's industry practice, it's what's being done. Then you have, again, reversed stress amplitude on this axis and the life on this axis for the same material. And you can see the enormous drop depending on temperature. And this is just getting warmed up. We're going to see a lot more interesting. So temperature, interestingly enough, proves to be key. We were talking yesterday, or rather we heard some interesting stuff yesterday about 3D printing, and the materials usually 3D printed. What I'm talking about is injection molded materials, extruded materials, or die-cast materials. So they differ quite a lot. But some of the basic investigations we did were, first of all, to look at the effect of frequency. So what you have on the vertical axis is the temperature. We always started out at 23 C being ambient, and then increasing the nominal stress for certain given frequencies. And as you can see, well, we wanted to investigate how low do we have to go in order to not see a temperature raise in the specimen, because we don't want to change that. We wanted to have isothermal conditions. Well, it turns out we have to go really, really low, 0.25 volts. If we do that, it takes forever to test the specimen. So we decided, okay, we'll ramp it up a little and see what happens. And it is not entirely unproblematic, because at, say, I'm going to go with the worst and say at 3 Hertz, you actually have a temperature increase of about 27, 28 degrees, which is quite massive. And this is not over a very long period of time. Before we go into the video, I'll point out one thing that has been universally concluded. There are 3 possible scenarios when you're working with plastics. What happens to the temperature? One is your loads and your environment are such that whatever you apply causes next to no temperature change. It increases slightly and then remains at a steady state level. The second is when you increase either the load or the frequency or whatever else drives it up, then you can reach a steady state temperature after a while and it stays there, which is more realistic, particularly when we're talking about variable amplitude loading. But what we haven't considered then is that temperature might actually fall and then it might actually rise again and so on and so forth. The third and worst scenario is if the amplitude is so high that you cause thermal failure instead of mechanical failure. That means that when you think of plastics, you have to think thermomechanically all the time. What I want to show you here is an example of uniaxial testing where we have applied a medium deformation amplitude. These are circular rods. The temperature is monitored by means of thermal camera. After 25 repeats, we start out at 20. We've reached, you can't actually see that because it rises slowly. What you're seeing now, after about 50 repeats, is that quite a large volume has attained quite the temperature. We're approaching 100 degrees C. And this is going very slow. Now we're at 110 degrees C. And this keeps on and on and on and increases. And this is merely after 100 repeats, so not a lot. It's just that the strain amplitude, or rather the displacement amplitude, is rather large. We go all the way up to 120 degrees C, which is quite interesting. That, by the way, is extruded nylon 66. Then, another aspect is that you need to look at what's the effect of just increasing the load amplitude. Because frequency is one thing, load is the other. You might actually have a constant frequency, but I can't really see which case that would be, but just in case. So what you see on the vertical axis here is the specimen surface temperature, measured in degrees C, the applied constant load amplitude, so not a realistic case, but for investigative purpose, this serves quite a lot. We apply a pulsating load of 3 Hz, and we see a near exponential increase in the temperature, which is not very good, because that you need to control. You need to understand where it comes from. So what happens if we now go to a different case where we increase the amplitude? If you want to convert this to strain, instead of displacement, this is an amplitude of plus minus 10%. Let's see if I can get it running. Here we go. Now what's happened to form is that, well, this specimen has been mounted slightly askew, that's why we're seeing a shear band. It's going into, well, almost buckling, but because this is a visco-plastic material, buckling isn't that big a problem. It's more bound by the geometry than it is of the massive bulk. I'd like you to observe this little location where a crack has formed and it closed, and then at some point, boom, we pull it apart. Now, if you observe the temperature at the end, it says 145 degrees C. There was a lot of skepticism, this is pretty old, this is some 10 years old, whether or not the FLIR camera did the right thing, because it's not easy to calibrate against plastics. So, being a bit overly experimental, that's how I would put it politically correct, I grabbed out and felt it, which was not a good idea. I ended up with a very large blister inside of my hand. It was scorching. So I guess that's a way to prove things physically, that they work or not. Now that's a specimen. That's one thing. But we have components, so we need to think a bit further. These are investigations that were conducted on a running spur here with a steel pinion and a plastic wheel. And the investigation was simply to see what happens when we reduce or increase the torque. So in this case, 100% is a maximized normalized torque. And what you can see here is with the rotational speed, with increasing rotational speed, obviously the line becomes much, much shorter. Now, that is something to bear in mind because when you have, well, we're all engineers, so I'm not going to start explaining what a gearbox is, what a gearbox does. But you know that it runs at different revolutions, different torques, and so on and so forth. It makes it quite a complex thing to investigate. So we wanted to see, well, what's the temperature going to be like? Now, I should add that these are grease lubricated gears, not oil, or not running dry. You can't run these things dry because then it fails very, very quickly. So, this is what that looks like. We start out, and at the beginning, the plastic wheel is on the left-hand side. That's somebody doing a bit of hand waving in front of the screen. But we start the process and it slowly starts to run. So the plastic wheel is on this side. That is why you first of all see a bit of reflection from the steel. Then as it goes along, this is about 200 revolutions per minute, the temperature focus shifts entirely over to the teeth, which is logical. They see a lot of work. And it runs on for, I think about 15, 16 minutes. And you can see the temperature that was at the beginning 23 C has now reached somewhere around 70. And any moment now, the teeth will break, and the section of critical look is about 80 degrees C, back. The teeth fractured. This, fortunately, turned into more of a mechanical failure than it was thermal. But sometimes you get plain thermal failure when the temperature is so high that the teeth just fold over like this. So that's to look at components. Then we have some geometrical peculiarities. I'm going to go back to the smooth sample. Unfortunately, you don't see it well yet because we need to start pulling it before the camera activates. But this is what goes on in a smooth specimen which is subjected to reverse loading. You can see it's very uniform. So I'm not going to bore you with this because it's not very exciting. But let's look at this thing instead, which is the uniaxial testing of a notched sample. where we're zooming in. And at the beginning, we have a fairly homogeneous distribution, and after a while, you can also possibly see the viscoplastic or the constitutive appearance of the lagging or of the lagging strain. But what happens is that all the heat is focused to the notch, and this serves as a plastic hinge. That's where all the heat goes, and that's why. Well, not just that's why, but that's one of the reasons why machine elements or design elements such as fillets and notches and so on are really, really critical places to look at in plastics. Of course, there are metals as well, but that's where you get the heat out of the mold. Now, interestingly enough, the temperature doesn't go up to massive values in this case. But that was because we did this fairly slowly, as you can see. There's no speed going. It's quite difficult to do. So, with that, let me jump to one of the favorite topics when it comes to plastic, and that's morphology. Because what governs the properties of the plastics is the structure. This is a microton cut of polyacetal, which has had fairly nice crystallization boundary conditions, you might say. What you see are elongated spherulites that are fairly large in the center. This is about 50 microns, and this is about 150 microns thick. And how they grow towards this, or rather, well, they seem to be growing towards the outer layer. This is the injection molding skin. That looks amorphous, and it's often classified as amorphous because it's transparent, which is not the case. It's highly oriented. When you shoot the molten plastic into the mold, it's got about the viscosity of water. Then it sticks instantly to the mold surfaces, boom, stretching all the molecules, and that gives you something which acts almost like a wrapping foil. Now, this wrapping foil is very important to keep in mind because it will prove one of the main indicators for why plastic parts fail the way they do. So what does this actually do? I do apologize. I would like to go through this in much more detail, but then we'd be stuck here until Sunday. So I'm hoping you will forgive me for that. What I will do instead is show you one example. This here is the ultimate tensile strength, in this case of polystyrene, on the vertical axis, and the degree of orientation of the macromolecules on this axis. This is an experiment that was conducted in 1974, so actually before I was born. It was quite interesting. Not because of that, but simply because it's interesting. And what you can see is that you can increase the ultimate tensile strength by simply stretching the fibers. Well, obviously, that's how it works. And that also leads you to, unfortunately, to draw conclusions that, well, all I need to do is stretch my fibers long enough and then I can reach infinite amounts of UTS. But of course you can't. Theoretically, you can reach some ridiculously, on a micro mechanical level, you can reach theoretical Young's moduli of, I think, close to 300 gigapascals for polyamide. But of course that doesn't happen because those conditions don't exist. The other important variable often used in semi-crystalline polymers is the degree of crystallization. And this is a diagram that shows the apparent Young's modulus. There is no Young's modulus for plastics, so let's just leave it at that. This is a secant modulus taken at some specific strain. And this is the degree of crystallization. Now, they're called semi-crystalline, but that doesn't mean they can reach 50% crystallinity, all of them. In fact, the degree of crystallinity can vary anywhere between from 20% up to 85%, depending on what the polymer is. Now what you see here is a non-linear relationship, so that with increasing degree of crystallinity, the modulus increases, but there is obviously a peak at some point. These are also things to bear in mind. That, in turn, it is basically, let me walk back and step further there. All of this morphological stuff is the reason for why when you talk about plastics, you cannot talk about integral properties. As in just pulling something tensile until it breaks, that's worth next to nothing. You need to look at all the different layers. We've done that. Unfortunately, I don't have the slide with me, but it's quite easy to show what the individual layers have in terms of stress-strain curves, which is the easiest way to show to people there is a big difference. Now, let me move on. And this is where I'm expecting some discussion afterwards, so that's good. Because my colleague and I were trying to find some generalization way when it comes to multi-axial particular plastic. It's tricky as it is. But we know that we have a unit volume, and this unit volume consists of distinguishable geometrical features. They look like spheres, they look like elliptoids, they look like shish kebabs, they look like discs, anything. And they are held together by a really strongly elastic wrapping foil. That's the injection molding skin. And what they also have is entropy elastic material between the boundaries of these elements. That makes it quite an interesting multi-phase material. The better thing is, we can categorize all of them, except for the wrapping foil, as flaws. And it's theoretically possible to assign individual apparent fracture energy to each of them. That's basically the attraction. And here's where most of the questions arise. The most likely place for any crack to initiate in an injection molded component is never on the surface, unless you compromise it. Unless you scratch the surface, you do something to it, the cracks will never start on the surface. They will start from within. That's the biggest problem. And a lot more notable authors than me have concluded so over the years. So it's something I've just happened to see for myself to the same extent. So if we look at the fracture behavior in a tensile specimen, this is typically what you use. This is what the plastic producers give you. Then we're going to have to talk about something called crazes. Crazes are basically a type of crack that form due to microvoids coalescing, being held together by fibrillar bridges. When these fibrillar bridges rupture, they open up a crack. Now, this nice little crocodile mouth here would essentially only come into play if I had a machine specimen, because then I don't have anything holding it together on the surface. In actual fact, this type of failure looks like this. And you can see on the length scale that we're talking about micrometers here. But this is a very simple cyclic kind of failure. It almost falls under the creep category. It's very hard to distinguish anything when you're talking about plastics, because if you're making life easy, you're applying sinusoidal loading, then you have a certain lag of the strain or the stress depending on how you control the test. However, there is never enough time for anything to rest. So when you're unloading, the time that you take to come down is never enough to fully reduce what's in there. So you have a constant increase of either your mean stress or your mean strain. You cannot avoid it. Here is probably the more interesting one. This is a fracture surface of this very specimen. And what's happened is that a lot of voids have coalesced over time to form a lot larger voids. So you're looking at the cross-section of that specimen. And they've started to grow radially outwards until they came in contact with the skin. The lobe was too large, bam, ripped it apart. We'll look at the fracture surfaces in a second. Another comment is, well, what about three-point bending? Three-point bending, you have a lot of stress at the surface, so surely you should see surface cracks. This is a type of, this is one sample from a three-point bending test that we did. And we can conclude, unfortunately, this is not magnified well enough, but the crack actually initiated under here and grew in two directions. But it wasn't until it grew through the skin that the process actually accelerated. So until it did that, it was quite all right. So, in a component then, this is not a very pretty picture on the left-hand side. This is a void. This is a void that we found after we looked at the fractured component, so we couldn't have seen it from the outside. We decided, okay, let's put it under a scanner, and see what this looks like. That's quite a nice little block. It's quite deep. And this is not something you would detect unless you're doing CT at the time that you're testing, or MRI for that matter. We tried CT, but it was a bit too difficult to assess during the sample loading, and also became hideously expensive. We ran out of funding. So that's a typical void. On the right-hand side, you see a failure where basically a tooth has broken off from a gear wheel. This is a typical craze failure. And when you look at that surface, or that fracture surface, this is what you have, which is pretty logical, following the actual mechanism. The craze opens up, and then it opens up on two sides, and then it just goes through. What's important with both of these, the material in itself is highly ductile. It's got a rupture strain of over 25%. But all the surfaces are brittle. There is no ductile failure. Because there is a degradation in fracture strength. So there is, you could essentially call it ductility exhaustion, but I don't like to use that word because it places us in the category of some thermomechanical elements. Okay. So in terms of multi-axial loading, then what are the consequences? This is an exhaust part. Well, not an exhaust. It's an intake manifold. This is an example from BASF, public domain data. And what I want to look at is an example situation, one singular point in time of any given load history. We're going to look at a couple of different points. I might have a point over here, which is the temperature T1. T1 follows this red line in the stress strain diagram. So that's one thing I need to think about when modeling. However, if I look at a different point, because this is a continuum, then I might have a temperature T2, which is a lot larger, so I need to make use of this curve if I'm to analyze it. And then finally, looking at a third position, the same case. So I need to be able to predict the temperature for every point in this continuum for the entire time. Then I know what I'm doing. Thank you.
It means it's going to be time.
Okay, I'm going to speed up a bit then. So, what we did in order to make sure that we had exhausted all the capabilities, we did a pretty careful review, a lesson analysis, which we found to be rather easy to deploy, something you could use for infinite life analysis. But unless you've got a proper way of predicting the temperature, that's pretty much what it's going to be limited to. But it's easy. It's a design tool. EN was much more tricky because all of the research, not just ours but out there, shows that you don't have stabilized rhesus loops. They don't exist. You have to purpose-made specimens for specific testing. You have self-eating, and there is no point in trying to measure strains using gauges. Because what you're doing is you are applying these gauges to the surface with something like epoxy resin or similar. Which means that for some plastics, what you are measuring is actually the glue and not the properties of the plastic itself. So if you want to do something, you have to use non-tactile measurement skills. Nothing else works. So, have I already come to a conclusion? Yes, I think I did. So in general, what we found in this case was that the life of injection molded plastics can't be successfully analyzed using neither EN nor SN. It's not possible. We see an opportunity in fracture mechanics thanks to all the geometrical functionalities and, well, going back to the morphological structure, that there are individual entities that we can isolate and investigate. That's one of the benefits of polymer physics. You can actually create these structures in a unified environment. We know that we can conduct these analyses in Abacus. That's obviously our tool. I guess if you have any other code that is similarly capable of doing fracture mechanics. Particularly my focus is, or our focus right now is on the extended finite element method. And that's where we're seeing actually rather promising results on the whole. But, to be quite honest, without an injection molded simulation up front, the subsequent structural and fatigue investigations are not very productive, to be honest. So the outlook is to combine a lot of different fields. It's necessary to do so. And yeah, it's going to be quite an interesting ride. I'm sorry to have rushed through all of this, but you've been a pleasant audience. You've not fallen asleep, or at least if you did, you didn't snore, which is greatly appreciated. And I'll now be very happy to answer whatever questions you might have, although it might take a bit of time. Thank you very much.